The Longevity Factor by Yuri Milner. In 1977, the Voyager probes were launched toward the outer solar system, each carrying a golden record containing hundreds of sounds and images, from the cry of a newborn baby to the music of Beethoven. In the emptiness of space, they could last for millions of years. By that time, will they be the sole representatives of human culture in the cosmos, or primitive relics of a civilization that has since bloomed to the galactical scale? The Drake equation estimates the number of currently communicative civilizations in the Milky Way by multiplying a series of terms such as the fraction of stars with planets and the fraction of inhabited planets on which intelligence evolves. The final term in the equation doesn't get much attention, yet it's crucial not just for the questions of intelligent lives, but also for the question of how to live intelligently. This is L, the longevity factor, and it will represent the average lifespan of a technological civilization. What determines this average? Surely the intelligence of the civilizations. The list of existential threats to humanity includes climate change, nuclear war, pandemics, asteroid collisions, and perhaps artificial intelligence. And all of these threats can be avoided. Some can be addressed here on Earth. Others require activity in space, but with the ultimate aim of protecting the planet. In 1974, Princeton physicist Gerard K. O'Neill published a paper, The Colonization of Space, which led to the first conference on the subject, sponsored by Princeton and Stewart Brand's Point Foundation, and to O'Neill's highly influential 1976 book, The High Frontier. This has been an inspiration for the current generation of visionaries who advocate steps such as the transfer of heavy industry into orbit, where it can run on solar energy and directs its heat and waste away from Earth, and the colonization of Mars. However powerful our local solutions, betting everything on one planet would be imprudent. Stephen Hawking has estimated, although the chance of disaster to planet Earth in a given year may be quite low, it adds up over time and becomes a near certainty in the next 1,000 or 10,000 years. By that time, we should have spread out into space. In the long term, Mars must be a stepping stone to more distant destinations, because two adjacent planets could be simultaneously affected by the universe's more violent events, such as a nearby supernova. We need to start thinking at the galactical scale. The first target might be the Earth-sized planet Proxima b, recently discovered orbiting the nearest star to the Sun, 4.2 light-years away. Sooner or later, we'll have to master propulsion fast enough to make interstellar journeys practical. Perhaps by that time, we'll have developed beyond our organic origins. It has been estimated that von Neumann's probes, robots that can land on the planet, mine local materials, and replicate themselves could colonize the entire galaxy within 10 million years. Yet, the renowned physicist Ashok Sen has recently suggested that even in the face of death bubble, there might be an escape route. The loophole is the accelerating expansion of the universe. In 1998, astronomers discovered that all galaxies not strongly bound together by gravity are moving apart even faster. This accelerating expansion will eventually carry them beyond one another's cosmic horizon, so far that even light from one can never reach another. Thus, they can no longer communicate. But, on the bright side, they can also never be swallowed by the same death bubble. So, by splitting into daughter civilizations and putting as much distance between them as possible, a civilization could ride the expansion of the universe to relative safety. Of course, another death bubble will eventually pop up within any cosmic horizon. So, the remaining civilizations need to keep replicating and parting ways. Their chances of survival depend on how far they can travel. If they can move at a substantial fraction of the speed of light, they will raise their chances of survival considerably. But even those that dispersed only far enough not to be bound by another galaxy's gravity, about 5 million light years, might significantly improve their odds. Such problems may seem remote, but they'll be real to our descendants. If we can survive long enough to allow those descendants to exist, our responsibility as a civilization is to keep going for as long as the laws of physics allow. The longevity factor is a measure of intelligence, the ability to predict potential problems and solve them in advance. The question is, how intelligent are we?